Welcome to GWA Physics, and this video that we're going to look at here has to do with roller coaster problems. Now, as you learned in class, roller coaster problems deal with the concept of conservation of energy. And so what we want to be able to do is we want to be able to solve for the energy at every single spot along the roller coaster. And what we should also remember is that energy is conserved, which means that the total amount of energy at any given spot should be the same as the maximum amount of energy that we have at the top of the first hill. So let's first solve for the energy at the top of the first hill. So we learned in an earlier video that the work done to get the car to the top of the hill will be equal to the change in its potential energy. So if I solve for the potential energy of the car as it comes to the top of the hill, then that's going to be equal to mgh. And so we've got 10 for the number of kilograms times 10, which is the acceleration of gravity, times 6, which is the height of the first hill. And 10 times 10 is 100, times 6 is 600. So we've got 600 joules of potential energy at the top of the hill. Now, what I'm reminding you of is that the amount of energy at any given point, if I wanted to know what the energy was right here, or as we've got it located, we want to know the energy right here, and we want to know the energy right here, and we want to know the energy right here, and we want to know this final energy right here. All of those energies, the potential plus the kinetic energy at any given point, should be equal to 600 because 600 is the maximum amount of energy that the roller coaster has in this particular problem. So what I have suggested is that we solve for the potential energy at any given point, and then all we have to do is subtract to get the kinetic energy. So if we look at this first position right here, that 10 kilogram car is 4 meters off the ground, so the potential energy is going to be equal to 10 times 10 times 4, or 400 joules of potential energy. Knowing that automatically tells me that the kinetic energy there must be 200 joules because they've got to add up to 600. Down here at the bottom, we're trying to find out the velocity of the car when it's 1 meter off the ground. Well, let's solve for the potential energy first. The potential energy is going to be 10 times 10 times 1, or 100 joules of potential energy, which tells me that the kinetic energy at that point must be 500 joules because they have to add up to 600. Now, we'll solve for the velocity in just a second. We look at the car at this position. It's 2 meters above the ground. So the potential energy is equal to 10 times 10 times 2, which is 200 joules of potential energy because it's 2 meters above the ground. So the kinetic energy automatically has to be 400 joules. And so that's the energy of motion for the car at the top of the hill. Now, last but not least, if you remember the slide problem, we said that the energy at the top of the hill will be equal to the kinetic energy at the bottom of the hill, and because we're at 0 meters, there is no potential energy, so all of the energy must have been kinetic at this point. Now, if that makes sense, let's go back and let's solve for these other values. Right here it says, what is the velocity of the car at this lowest point here at 1 meter above the ground? Well, the kinetic energy is 500, so we're going to do 500 joules is equal to 1/2 of mv squared, which is the equation for kinetic energy. And so if we grab our calculator, half of the mass, which was 10, would be 5, so we're going to divide by 5 to both sides, like that. That's going to give us 100. And then when we take the square root of 100, of course, we know that the velocity there is going to be 10 meters per second. Now you could solve for the velocity at any other point on the roller coaster as long as you know the kinetic energy. And I think that the way that we've gone about solving for it is the easiest way that we can do that on our papers. Now, if you have any questions, come and see me. Otherwise, thanks for watching the video.